Alright, let's begin. Today we are going to start learning about rotational kinetic energy. So remember, the kinetic energy was the energy in motion. So rotational kinetic energy means the energy in motion around a circular path. The energy in motion around a circular path is called rotational kinetic energy. We were using the expression 1 over 2 mv squared to find the kinetic energy. Here, instead of m, we are going to use moment of inertia, and instead of velocity, we are going to use a angular velocity. Okay, these two are going to be our variables for the rotational kinetic energy. Okay, so if the moment of inertia of the object is larger, then what's going to happen? The mass will be larger, so object will get slower, obviously. If the angular velocity of the object is larger, that means the object is going to get faster and it's going to have more kinetic energy. So let's go to the formula. You know that one solid body consists of more than one tiny particles. So that's why there are many particles inside of the a solid object, a rigid body. We call it a rigid body. So to find the total kinetic energy, we are going to use at the bottom, as you see at the bottom, there is total kinetic energy. Just let me get my pointer again. Here at the bottom, to find the total kinetic energy, we are going to use 1 over 2, m1 r1, m2 r2, m3 r3. How many bits you have from the solid object, you are going to put all of them together, and the object's angular velocity square. When you take it, you are going to find the total kinetic energy for the body. Okay, let's move on to the formula. Our original formula will be this. This is going to be our kinetic energy formula for the rotational bodies, for the rotating bodies. So rotational kinetic energy will be 1 over 2 moment of inertia, and times angular velocity square. Okay, angular velocity square. This is going to be our formula for the kinetic energy. Okay, let's move on. Let's check the physical quantities here. Physical quantity for linear motion and versus rotational motion. For linear motion, we had displacement. As you know, displacement. The SI unit of displacement was meter. And here, for the rotational motion, instead of displacement, we have angular displacement. We use theta as a symbol, and the SI unit of angular displacement will be radian. Okay. For the velocity, we had meter per second. Now, for the rotational motion, we are going to have angular velocity. We are going to use the omega, letter omega, to symbolize angular velocity. The SI unit of angular velocity will be radian per second. Okay. For the acceleration, we had meter per second square. We used to symbolize with the a, small a. Now we have angular acceleration. We are going to use alpha, Greek letter alpha, to use the angular acceleration, and the SI unit will be radian per second square. We had mass for the linear motion. The SI unit of mass was kilogram. Now for the rotational motion, we are going to have rotational inertia. We're going to use capital I to show the rotational inertia, and the kilogram meter square will be the SI unit of rotational inertia. It is totally different than the mass, as you see when you check the units, when you check the dimension. Their dimensions are totally different. When we come to the linear motion, for the force, we had Newton, SI unit. Now we are going to use the torque, that is torque, letter torque. We are going to use to symbolize torque, and Newton meter will be the SI unit of torque. Okay, Newton meter. So let's compare. Now we can compare the quantities. Now let's compare the formulas that we have learned already for linear motion. For linear motion, remember we had the velocity u plus at, initial velocity plus acceleration times time. Now it is going to be in the rotational motion. It's going to be final angular velocity equal initial angular velocity plus angular acceleration times time. The formula will change like that. Here for the displacement or for the distance, we had ut plus 1 over 3 at square. Now for the displacement, angular displacement is going to be, we are going to have initial angular velocity times time plus 1 over 2 angular acceleration times time squared. Okay? Here to find the final velocity, we were using like initial velocity square plus 2as. On the other hand, for the rotational motion now, we are going to have, for the final angular velocity, we are going to use initial angular velocity plus 2 times angular acceleration times angular displacement. To find the displacement, we were using this formula, initial velocity plus final velocity times time over 2. Now, for the displacement again, we are going to use angular displacement here. For the angular displacement, we are going to have initial angular velocity plus final angular velocity times time over 2. These are going to be our main formula. So now let's move on to a question. There's a question I prepared for you. Let's practice some of these formulas on the question. Okay. So the question, before starting the question, what is positive anti-clockwise and negative? What is clockwise and anti-clockwise? One object rotates anti-clockwise. We are going to show as positive. It is going to be a positive torque. When object moves clockwise, the torque this time will be negative. Okay. When object moves anti-clockwise, the torque will be positive. When the object moves clockwise, the torque will be negative. Okay. So let's check the question here. You're on a big wheel at the fairground, which makes one revolution every 10 seconds. One revolution every 10 seconds. What does this mean, first of all? One revolution every 10 seconds means this is the frequency, 1 over 10 frequency, or 10 seconds, one revolution means this is going to be the period, okay? T. This is going to be our T, period, 10 seconds. If you use the frequency, it is going to be 1 over 10, but remember, for when there is one complete turn, that is going to be a period. So 10 seconds take to complete one revolution. So this is going to be our period, okay? So the operator of the wheel decided to stop the wheel by applying the brakes. The brakes produce an acceleration of negative 0.25 rad per second square. Your seat is 8 meters from the axis of rotation. So this is going to be our radius over here. This is going to be our angular acceleration, radius. So first question is asking us, what is the angular velocity of the wheel? To find the angular velocity, what do you do? Angular velocity equals 2 pi over t, right? You can take pi 3 here. So let's put it here. 2 times 3 over. What is our period? We found the period over here. It is 10. So 2 times 3 over 10, that is going to be 6 over 10. It is going to be 0.6 rad per second, okay? This is going to be our angular velocity, okay? So what is your velocity? Your velocity before the brakes are applied? So before the brakes are applied, we are going to have linear velocity. How do we find linear velocity? Let's put it here. B. Linear velocity equal angular velocity times radius, right? So our angular velocity we found 0.6 times, what was the radius? It was 8 meters over here. So when you multiply it, you're going to find linear velocity 4.8 meter per second. Okay? Meter per second. That is going to be our linear velocity. So how long does it take the big wheel to stop? So here we are going to use the equation that involves initial and final angular velocity. Let's go back a little bit. Which equation can be applicable for this? It has both initial and final angular velocity, and it has angular acceleration and time. Which one is going to be applicable? Can you guys tell me? Look at the first one. The first one. It has final, it has initial, it has angular acceleration and time. So we're going to use the first formula to apply for C. Okay? So let me change the page and let's do the C, the other page. C. So the formula will be final angular velocity equal initial angular velocity plus angular acceleration times time. Okay? So we found what did we find the final one? We can use the V over here. If we find the V, this one we can use as final one. Okay? Because before stopping, it's going to be that is going to be the our velocity that we are going to look for. So let's put it here. We are looking for time. So time equal V2. So let's crisscross them. Let's send V1 over omega, right? Yeah, that is going to be our formula. So to find t, our final velocity was 4.8 minus our initial velocity. What did you find? 0.6 over what is our angular acceleration? Negative 0.25. Yes, negative 0.25. So when we do this, we are going to get our acceleration. Let's do that. 4.8 minus 0.6 is going to be 4.2. Negative 4.2. So 4.2 over 0.25. Yeah. So it's going to be 16.8 seconds. Okay? All right? Yeah, 16.8 seconds. It is going to be our answer. Okay? So let's go back. What is the asking us? How many revolutions does the wheel make before it comes to stop? So to find the revolution, first what we have to find? First we are going to find displacement. To find the displacement, let's go back. To find displacement, which formula we should apply to find the displacement? Look at formula number 3 here. We have final angular velocity, initial angular velocity, we have angular acceleration, so we are just going to look for displacement. Okay? So let's find the displacement first of all for the. So to find the displacement, we are going to use this formula: v2 square equal to omega 1 square plus 2 alpha theta. Okay? So this is let's develop the theta. Theta equal what's going to be omega 2 square minus omega 1 square over 2 alpha, right? So to find theta, again, 4.8 square minus 0.6 square over 2 times negative 0.25. Okay? So let's find the answer here. Let's find the answer. So 4.8. So 20 over 0.5, that is going to be 40 rad per second. Okay. 40 rad per second it's going to be. So here, you know that one revolution is 2 pi, right? One revolution equal to 2 pi. So what about 40 2 pi rad? What about 40 rad? So it's not really second, it's going to be just 40. What about 40 rad? How many revolutions it will be? You can take the pi again, 3. So it's going to be 40 over 2 times 3. It's going to be 40 over 6. When you divide the 40 to 6, it's going to be 6.67 revolution. Okay. So the object will cover 6.67 revolution with this angular velocity and the acceleration. Okay. Any questions? You guys have?
No.
Okay. All right. Let's move on then. This is it for the question. Let's move on to power in rotational motion. So to find the power in rotational motion, we are going to use torque times angle moved through it, or angular displacement. Okay, torque times angular displacement. Here, angle moved through. That means angular displacement theta. So that is going to be our formula to find the work done over here. To find the power, remember power. Power was the ratio of work to time, right? So instead of work, let's put torque times displacement, and our formula for the power will be torque times displacement over time. The SI unit of power, again, the SI unit of power will not change. It is going to be SI unit, let's say, SI unit still is what? Okay? The SI unit still is what? And remember, this Q over T, what does this mean? Angular displacement over time. What does this mean? It means angular velocity. When we replace it here, theta over t, the formula will be torque times angular displacement. This is going to be our formula. Torque times angular displacement will give us power. Okay? Torque times angular displacement will give us power. Right?
Okay.
All right. Let's move on. There's a question. A mechanic applies a torque of 200 Newton meter over a half turn and takes 6 seconds. What is the power? So what does half turn mean, first of all? Half turn. What is the displacement here for the half turn? For the half turn, what is the displacement? Can you tell me?
2 pi
It's
over
going to
2.
be pi, right? Normally, a whole turn is 2 pi, right? Or one revolution is 2 pi. So that means a half turn will be pi. Okay? And we have a time which is 3 seconds, 6 seconds. And we have torque which is 200 Newton meter. So to find the power, what are you going to do? Power equal torque times displacement over time. Okay? So our torque is 200. We can take again pi as 3 over 6 seconds. We can simplify them. It's going to be 2. So it's going to be 100 watt. Okay? The answer will be 100 watt for the question. Okay? So let's move on to parallel axis theorem. So parallel axis theorem tells us to find the center of mass for the object. Okay? Find the center of mass for the object. There is a simple relationship between two moments of inertia. So we are going to use this formula, IP equal ICM1 plus md square to find the moment of inertia, the common moment of inertia for the two parallel objects. This IP stands for moment of inertia, the axis parallel to the one used to calculate moment of inertia about the center of mass. And ICM stands for moment of inertia about the center of mass. M is the mass, and D is the displacement from IP to ICM. Let me explain it here. As you see, there are two objects over here. The distance between them is called D. This IP stands for the object's moment of inertia. ICM is the moment of inertia at the center of mass for the object, as you see here. Let's say we have a rod over here. The IP stands here, the moment of inertia for the body. Then the moment of inertia for the center of the body, ICM. So to calculate the moment of inertia for the rod, we are going to use this formula: 1 over 12 plus 1 over 12 ml square plus. Since when you divide the object into 2, it's going to be L over 2. This is going to be the distance. This is going to be D. md square, remember? So ml over 2 square. When we add them, we are going to get the 1 over 3 ml square for a simple rod. When we apply the parallel axis theorem to the rod, we are going to get this for moment of inertia for the rod. Okay? All right. So, any questions so far?
Yes, Mr. I didn't understand this part.
Okay, this part, first of all, this is the moment of inertia for the rod normally. Okay? This part, 1 over 12 ml square. This is our ICM. ICM. It is a variable, you can say. It is like this always. Okay? ICM for a rod, it's always 1 over 12 ml square. Okay? Our mass for the rod is m. Okay? For this rod, for this part, this one, the rod that we are talking about. Okay? The mass of the rod is m. We consider as m. And L over 2 comes from here, the distance from ICM to IP. Okay? The formula is here, right? The distance is d. It comes from there, okay? So when we put them over here, it's going to be 1 over 12 ml square plus m times L over 2 square, okay? Into parentheses. This is our distance, displacement, like distance between these two ICM and IPM, okay? So when we add them over here, since they are not in the same, what do you say? They are not like fractions. We have to make them like fractions. So 1 over 12 will be here. So when we multiply here by 3, it is going to be 3 over 12, right? Since both of them have ml square,
yes,
you don't need to add them, just we are going to add simply 1 over 12 plus 3 over 12 is going to be, so that is going to be
4 over 12
ml square. When you simplify that by 4, it's going to be 1 over 3
1 over 3
ml square, okay? All right. So, we have a question over here. Let's go to the question. They're going to apply the same formula here. Okay. So, here the question is asking us about a body of mass 4 kilograms. So the mass is 4 kilograms. Let's put it here, the given. Has a moment of inertia about its center of mass 10 kilogram meter per second square. So the moment of inertia at the center is 10 kilogram meter square. So we are going to use it ICM. Okay. 10 kg meter square. It is then rotated about an axis which has a displacement of 403. So 403 means displacement. 403 means it is in 2 dimensions. So we have to, we are going to apply the Pythagoras to get the d. Okay. When we apply the Pythagoras for the d, we are going to get the common d for that, like resultant d. We are going to find. Okay. So let's first find the resultant d.
Okay.
Then we are looking for IP. Okay. So let's find the resultant d. Apply Pythagoras. Okay. Apply Pythagoras. So let's say d square equal. Let's put d square, not d equal. So d equal 3 square plus 4 square, right?
4 square.
So d will be equal 3 square is 9, 4 square is
5.
16. So the d will be
5.
5. You can say, what is it? Centimeter. It's giving meter already. So 5 meter. So we find our d. Now let's put the formula. IP equal ICM plus md square, right? Okay. Our ICM is 10 plus, what is our m? M is giving us 4 times 5 square. Okay? So it's going to be 10 plus 4 times 2500. So it's going to be 110 kilogram meter square. Okay? 110 kilogram meter square. It's going to be a moment of inertia of the body. Okay? Any questions?
No.
All right, let's move on then. So angular momentum and angular impulse. We have only 5 minutes, I think. We will continue. Hopefully, it won't stop. So angular momentum. Again, angular momentum was a product of mass and velocity. You guys remember? Mass and velocity. So for the angular momentum. Sorry, this momentum was a product of mass and velocity. So to find angular momentum, here we are going to use L instead of angular momentum. We are going to multiply R times P. Okay? When we replace P here, when we replace it by mv, our formula will be m times r times v. It's going to be our new formula. Okay? So here, the angular momentum at the bottom, as you see, it is going to be r times m times v sine theta. If there is an angle between the radius and the velocity. Okay? If there is an angle between radius and velocity, we are going to use sine theta because it is going to be perpendicular, it's going to be vertical. Okay? I'm going to show you a shape over here. As you see, axis of rotation for the angular momentum. It is L over here. You can apply right hand rule here. The L will be your thumb when you put it here. The R will be your index finger R, and the P will be your middle finger when you apply the right hand rule to moment of the angular momentum. Okay, so angular momentum will turn into here the formula here. Instead of V, what can we write? Instead of V, we can write omega R, right? Omega R we can write. We can replace it with omega R because the linear velocity equal to angular velocity times radius. Okay. So when we replace it here, the formula will turn to this: mr square omega. So mass times radius square times angular velocity will give us angular momentum. Okay. Remember, mr square means what?
Okay.
Another point. Mr square means moment of inertia, right?
Moment of inertia.
Yeah.
Moment.
So we can moment of inertia for a point. So we can replace it with the I. At the end, our angular momentum will turn into this: moment of inertia times angular velocity. Okay. So the SI unit of angular momentum will be kilogram meter per second, kilogram meter square over second. That is going to be the SI unit of angular momentum. Okay. What was the momentum for momentum unit SI unit? Do you guys remember? Momentum SI unit?
Kilogram square.
Kilogram meters per second, right? But here it is kilogram meter square over second for angular momentum. Okay? It is going to be a different dimension. All right? So let's go to angular impulse. Angular impulse, the change in angular momentum of a rotating body caused by a torque acting over a certain time. Okay? So it's going to be angular momentum will be the change in angular momentum, over time. Okay, the change in angular momentum over time will give us the angular impulse. Okay, so remember the angular momentum we just found moment of inertia times angular velocity. So moment of inertia times angular velocity over time will give us angular impulse. So angular impulse, let's put it here. Impulse equal to moment of inertia times angular velocity over time. That is going to give us angular impulse. Okay? So torque will affect on the angular impulse. If there is no torque, there is not going to be angular impulse again. There should be torque acting on the angular impulse. Okay? So conservation of angular momentum, it is as the same as we learned in previously about the conservation of momentum. If there is no resultant force, we were saying, and the momentum will be preserved or conserved. Here, instead of force, we are using torque, resultant torque. If there is no resultant torque acting, the angular momentum of a body cannot change. Okay, so the final momentum will be equal to initial momentum. Okay, so to find the final momentum, we're going to apply final moment of inertia times final angular velocity, initial moment of inertia times initial angular velocity. When we do this, we are going to find any property or any like physical quantity over there. Okay. So next and lastly, we have center of mass of a rigid body. This topic, I think you guys had difficulty to understand this topic. So there is an example over here. Let's go to over the example. There are two bodies over here. One of them has 2 kilogram, as you see over here. The other one has 3 kilogram. The distance between A and B is 50 centimeter, and the distance from A to P is 20 centimeter. There is a force acting like opposite direction of the two masses over here. Okay, it is opposite the masses, oppose the gravity. Okay, and why it opposes the gravity? Because if it doesn't oppose the gravity, the system will not be in balance. That's why it has to oppose the gravity. Okay, so let's first find anti-clockwise moment. We are going to use here P equal x times f. X times f. X is this distance from P to f. Okay. So clockwise moment. Let's find the clockwise moment. Clockwise moment means we are going to use A and B over here, as you see. So xa times ma times g plus xb times mb times g. Why we add them? Because look at A and B, they are in the same direction. That's why we have to add them. Okay. So when the rod is balanced, this time F will be MAG plus MBG if the rod is balanced. And then let's go over here. Let's go over here. We can look at the, we can like send the MAG and MBG over here. And when we send it, we are going to find, we are going to have this formula over here. Okay? Next step, let's leave alone the x and find the x. When we leave alone the x, the formula will turn into this when we leave alone the x. So instead of f, let's replace the f with this MAG plus MBG. When we replace the f with MAG plus MBG, the formula of the x at the end will be this. Okay, we are looking for x, by the way, here for x. The distance from a point out of the system to the force applied on the system. Okay, when we put the whatever we have over here, when we have, oh wait, just a second. Okay, so when we apply here, when we put whatever we have into the formula, our XA, what is our XA? It is 20 centimeter, which is 0.2 meter. 20 centimeter, XA, this is our XA. Our XB is going to be 50 centimeter, which is going to be 0.5 meter. So 0.2 times 2 kilogram plus XA times MA, let's say, XB times MB. Okay? When we multiply these two plus these two over MA plus MB. Okay? MA plus MB. When we add them, at the end we are going to get 0.38 meter. What does this mean? This means the force needs to be applied 38 centimeter from the left hand end of the rod. When we apply this, the object will stand properly, or it will stand, what they say, in balance. Okay? If you don't apply 38 centimeter from the left, if you don't apply the force in that extent, the object will fall down. Okay, it is not going to stand. It is going to fall down and find its center of mass. All right. So that's it for today. Do you guys have any questions? This is the end of the unit, by the way. We finished the unit. You guys have any questions?
No.
Okay. Okay then. So this is going to be end of the unit. Tomorrow I'm going to post the quiz. Okay. Quiz basically, I'm going to divide your quiz into two parts. One part will be till kinetic energy part. Okay. The second part will start from kinetic energy and the end of the unit.